Okay, I'm going to try to explain how multiple bonds form and a little bit more about bonding terminology. So if you sketch out the orbitals for carbon, so like here's the 1s, which is not part of the valence, but if you look at the 2s, there's some s orbitals there, and then you have the 2p. And if you start counting, carbon has 4 electrons in its valence. And so we get this kind of arrangement like this, where the 2s appears full and the 2p appears to have a couple of unpaired. And it'd be hard to say which orbitals they're actually in. We usually just put them in the first one. It looks like the statement that I have up here that there are 2 different states for electrons in its valence. What I mean is that from an energy point of view, the 2s is at a slightly lower level in energy than 2p. Also, if you look at the 2s, they appear paired, and the 2p are not paired, and so that is also a difference that we got to deal with. Okay, I love that pause function. So anyway, we're talking about, before I get interrupted there, that really you have some paired, you have some unpaired, you have some in the 2s, which are a little lower in energy, some in the 2p, which are a little higher. The only problem with this is that, like, if you look at methane, which we have drawn a few times, let me grab that dude here. I've got one of the little ball and stick models, you know, the tetrahedral shape here for methane. The way this bonds, there's no difference in the 4 bonds. We have the tetrahedral geometry, all the angles are 109.5, all the bond lengths are the same, all the bond strengths are the same. So experiment does show that, and that's not really consistent with what I have on the screen right now. So this is what happens in science. We might need to either abandon the model, well, what would that be like, to have to just throw out what we've had, or perhaps we might be able to refine it a little bit and make it fit a little better. So with that in mind, what kind of things might we be able to do here? Well, if we go back to the idea that in some atoms the s and p orbitals, like, you know how Bohr said it was all just one big happy energy level? What if, in fact, like, he was kind of right? So let's see here. I don't know that I can resize my window right now. Let me try this. There we go. Now you guys should be able to see that. What if we go back to the idea and we take like somewhere in between S and P, we figure there's a blended level that's there. It would be somewhere between an S and a P level in its energy. It would be somewhere maybe even in shape in between them. And the resulting orbitals would be a total of 4, because that's how many we got to work with in the S and the P. So in 2D, we can actually draw what the level would look like. I will sketch it up here. Instead of, you know, like what we've got here with a separate S and P level, let's blend that together and let us have, now I'm going to go ahead and try to put a shape to them. They're kind of round, but they're kind of 2-lobed. Now why would that be? Well, it's because, that one I made a little skinny, but maybe not, that might be how it looks. These would be called Sp2 Hybrid orbitals. There would be one energy level, all at the same, you know, all at the same level here, the same degree of energy, and they would all be equal. So I didn't do a great job of drawing them because I made this one look like crazy wide here. But you know, if they all are kind of, I don't want you thinking they're all different. These would be 4 equivalent orbitals that could orient themselves around the central atom with equal bond lengths, with equal energies, with everything equal. So we actually believe that this is a model within the localized electron model that we try to use. Here is a little graphic showing that in 3 dimensions we might end up taking the S and the 3p orbitals, and I pulled this one up because this actually shows the shapes of like an S level and all the different orbitals in a P. And this tetrahedral looking picture here might give us some kind of an idea of how they would arrange around the nucleus. The nucleus would be right down here in the middle, and there'd be one up and out that way and down and back, all with the 109-degree bond angles. Here's another representation that might help you visualize this better. This would be like a single Sp2 hybrid orbital. You can see it does kind of have the shape I was trying to draw there. And then when the four of them are oriented around the central nucleus, we do get the tetrahedral arrangement that by now I hope is becoming kind of familiar to you. So we believe that the valence level might blend, and we do that, we modify our model because this is the way methane acts. It acts this way. So we're trying to make our model fit reality. There are several molecules that are based on this shape. They are all based on tetrahedrons. In other words, the electron geometry is tetrahedral, but because some of them do have lone pairs, they do get different shape names. For example, methane is one that we are well aware does that. Ammonia has tetrahedral geometry on its electrons, but because of the fact that the molecule itself only contains the 3 H's hooked at the end, we call that one trigonal pyramidal. Water, you may recall, we call bent. Here's kind of an interesting one. Let me see if I can drag it up just a little bit. This is F2.
Jeremy Duncan, to the office. Jeremy Duncan.
We kind of actually believe that even in fluorine, it's possible that the orbitals do something similar to what we're describing here, and that the little sharing of the electron pairs actually taking place between some Sp3 orbitals. In ethane, C2H6, we got a carbon and a carbon, and you can see that this carbon right here is basically like methane. It's tetrahedral. It matches kind of this arrangement, but they are overlapping their orbitals a little bit. So instead of just like a generic cloud where they can go any direction, we're now getting down to this idea that there are certain orbitals that might be involved in the bonding, and that helps us understand actually what's going on with multiple bonds. So, okay, so we have a guest star who popped in. Bring the desk back.
Bye.
Bye, Miss Valley. We have all kinds of celebrities pop by the studio here.
Bye.
So if you'll notice here, all of these on this page show kind of the electron pair is right in between the two nuclei. So it's that sigma bonding kind of a thing. It's typically like an end-over-end overlap where they're directly coming in between the two nuclei and shielding them from each other. And this term popped up on one of the sims. This kind of a bond is called a sigma bond. So some of the other shapes that we've learned are a little simpler. They only have like, maybe 3 clouds or 2 clouds. And that's where we get like trigonal, planar, and linear kinds of things. And in order for those to work, if you think about it like the sulfur trioxide when we did, they've got to have at least one double or triple bond in them somewhere to do that kind of thing. Those extra bonds, like anytime you have like a single bond, it's going to be a sigma type bond. But if you go to a double bond, there's going to be what we call a pi bond in there. And they actually explain like why unsaturated fats are better, to why we get a lot of energy out of acetylene when we burn it. So the question becomes, how do we get this kind of bond to form? And the localized electron model here with hybrid orbitals works pretty well, but we've got to allow for several possibilities. So consider the molecule here that I'll drag up onto the screen here just a little bit. In each case here, the carbon is only using 3 of its orbitals to hybridize. So if you look at what's going on, like over here, you've got an S and you've got a couple of the p orbitals, and they go together and they make these Sp2. Now they're Sp2 because we're only using 3 orbitals, an S and 2 p's. They're 1 part S and 2 parts p, and they're kind of arranged around the central nucleus like this. So what happened to the p orbital? that like didn't hybridize, that didn't participate. Well, this picture is not real 3D. I got a better one I'll show you in a second that gets more 3D with it. But this one does kind of label everything well. Here is one of the Sp2 hybrid orbitals, and that's where an H is forming a sigma bond to be on the molecule of C2H4. Here is another one doing the same thing. Now remember, down here on this red picture, we made 3 of these. One of the 3, right here, so like here's where those 3 are located. One of the 3 is end over end shielding type thing here, shielding the 2 nuclei from seeing each other, and that's like your regular sigma bond that's like every kind we've seen so far. The 2 p orbitals, or I'm sorry, they are in level 2, but there's only one of the orbitals. Here's one of them, and here's one on the other carbon. They do this side-to-side overlap where, yeah, the electrons are down in here, but they aren't directly between the nucleus like they are on a sigma bond, and they are a little bit more delocalized. They can move around just a little bit more within here and be either above or below. This would actually be a double bond. And when this happens, the carbons are in what we call the Sp2 hybrid state. That allows them to have 3 things hooked to them. The H, and the other carbon. This guy's doing the same thing. And so the unhybridized p orbital is going into the multiple bond, into the double bond. This picture is maybe just a little bit of a more of a 3D thing. Notice how like here this red shows the p orbitals that like didn't hybridize. So like the bond to the H, that's a sigma, sigma here. Those are the Sp2 hybrid orbitals at 3 out of the 4 available orbitals. And then these unhybrid P's, we believe, might blend together side to side like this. And so the electrons, there's only a pair of them. This almost looks like a triple bond to some people, but the above and below, that's just one p orbital sharing with another p orbital side to side. And so this is just a double bond. But this does put a few extra electrons in the space between the nuclei in here. And it does pull the carbons into slightly shorter bond lengths, which we saw from the sim, that double bonds will tend to have a little bit shorter bond lengths, and that means they have slightly higher bond energies also. Here's a kind of a nice 3D view of the thing also. It's just really, the same thing shown a different way. Notice how the double bond between the carbons has a sigma bond and a pi bond. And that's all it's listed, sigma pi, because that's just one sigma and one pi. Now, with all those electrons, they're real reactive there due to there's no atoms sticking out in that part of the thing because there's just a lot of electrons in the middle. And so that allows, there's a lot of stored potential energy there, and there is some really, really active chemistry that takes place. Triple bonds are really just a little bit more, just take it one step farther. There are 2 orbitals that hybridize, so it's in what we call an sp state. And there are then 2 p orbitals that don't hybridize, and they make the 2 pi bonds that are going to help make up the rest of the triple bond. So you have 2 orbitals that hybridize, sp, and the other carbon's got the same thing, but this is going to have a triple bond. There's only going to be one H out here and one H out here, and then we're going to have the top ones, the px's, side to side, and the py's, which are kind of out front and out back. They're going to do it like twice in order to get there. This side to side kind of overlap here kind of looks like this in 3D. The yellow in here shows like the sigma bonds from the hybrid orbitals between the carbons and between the C and the H. And then the blue and the purple here are showing, they kind of got it turned a little bit on angles to see it better. But those are the 2 pi bonds. This would be a triple bond, and this would be acetylene, which is very, very active stuff. And of course is the gas used in cutting torches. So we could take our chart a little bit farther. I'm going to kind of stop here for a minute because I'm running close to the time limit on this video and I don't want to go over it a lot. But our chart that we've kind of made where we looked at like how many bonds and how many pairs and how many clouds of electrons, how many domains, and it helps us determine the shape. We can actually tie that a little bit to this and figure out that there's a relationship between how many things are around the middle and what hybrid state it's got to be using. So I will deal with that a bit later because this is enough for one video.